speaking about the wave equation in electromagnetics. This is one simple example of a wave equation when a pulse is moving along x-axis here. So the displacement of this pulse at any time can be attributed to the time derivative or the spacing derivative partial x square. So the time derivative of this displacement u is proportional with some constant to the second derivative of the displacement with respect to x-axis. This is very similar to what we do here in electromagnetics. So what we are doing here is that we are trying to solve the Maxwell equation in a boundary value problem. We are trying to find the solution for the differential equation in some boundary for some region by deriving some field, electric field and magnetic field, and the solution should satisfy the boundary condition and should satisfy Maxwell equation. The solution of Maxwell equation is not easy due to the coupling nature between E and H in both Ampere's law and Faraday's law. We have E and H in each equation in Faraday's law and Ampere's law. So we played with the equation using vector analysis until we reached to a very simple equation, which we call the wave equation, which we started to solve last time. So this is the wave equation for Ex, for the X component of the electric field. It is del square Ex. Del square here is the Laplacian operator, and the beta square, beta here is the phase constant in radian per meter. So we need to solve this equation to find Ex. Ex, we can expand the Laplacian operator for scalar quantity. Ex here is a scalar. We can use this operator with vectors and with scalar. Here we have Ex as a scalar quantity, so we are going to expand the Laplacian operator. One easy way is to use the separation variable. So we are going to separate x and y and z function as f, g, h, then substitute this definition in the original equation, and we have reached to this equation down here. This equation is saying that 1 over f, which is function of x, d square f by dx square, all of this is function of x, all of this is function of y, all of this is function of z. And the total of this function of x plus f of y plus h of z, or this function of z, must be equal to some constant beta. Beta here is constant. What is the differential of beta here? Beta is the phase constant, right? Which is omega over the wave velocity, which is omega root mu epsilon. So beta is constant based on the frequency and the material property. So if we say that these three different functions should add up to some constant, so each one must be constant. Right? And the final answer of this must be some constant, which I can call minus beta x square, minus beta y square, minus beta z square. It turns out that these constants are the x component, y component, z component of the vector, wave vector beta. Beta now is a vector that has three components. Beta, the propagation constant now, is a vector that has x component and y component and the z component. These three components, the square of these magnitudes must be the same as beta square. What does this mean? What does this equation mean? When we say that beta is a vector with three components, this equation basically is called constraint dispersion equation. Dispersion because we have here relation between beta and omega. The relation between beta and omega is governed by this equation. This means if the wave propagation, if the direction of beta change with time, it must be the square of beta square plus beta y plus beta z must be beta square. So regardless of the direction of beta, at the end of the day, there must be some restriction on beta x and beta y and beta z. For any different value, they must add up to beta square, like this vector. Look at this vector. So beta here is some direction defined by beta x, the x component, beta y, and beta z. If beta moves to another place, we will have different beta x, beta y, beta z. But again, the square of beta x square, this equation must be verified even with the new beta. This means the vector beta, the tips of this vector must lie on what? Based on this relation that says that the total of this beta square plus beta y plus beta z must be beta square. So if beta x, beta y, beta z become any new value, they must verify or define vector beta on a sphere, on a spherical surface. It must have the same radius, beta. Okay, it's like vector that change direction based on the XYZ component, but at the end of the day, the vector direction must end on a spherical surface. So we call it concentric equation. This means the value of all the component must add up to beta square, and we call it dispersion because there is a relation now between the wave velocity and omega. In fact, the wave velocity here will be based on omega, so we call it dispersion relation. Does this make sense? Okay, and also this table is very important because it defines the behavior of all the solution of this wave equation based on the definition whether it is traveling wave, standing wave, or evanescent waves. For example, if we are solving the wave equation in Cartesian coordinate for this structure where we have like metallic hollow tube, we call it waveguide. So it will guide the wave to propagate through this hollow tube. In this case, if we are going to choose the solution along x and along y and along z direction, so f of x has two definitions. One defines traveling waves. Traveling waves when we have complex exponential. Whether you have e to the power j, this means this wave will be traveling. If you have cosine and the sine, this means it will not move with time, but it will go up and down. It will change by x and the time, but moving up and down like standing wave. And this will be clear after you find the instantaneous form. This is a phasor form, time harmonic. If you want to find the instantaneous form, you take the real part of this guy, e to the power j omega t, then sketch this function versus time or versus the space at different time. It will show that this wave is really propagating because it does have some complex exponential, and this wave is moving up and down. So we have a traveling wave and a standing wave, traveling wave, standing wave. So each solution, FGH, can be represented as traveling wave or standing wave. And also we have showed this last time, if you remember, we have showed here, if we take this part only, if we assume that the wave along x direction and y direction are standing wave, for some application we are going to have this. So along x and along y we have standing wave, and along z we have traveling wave, which is traveling along positive z because we have e to the power minus j beta. This is the time harmonic. If you find the instantaneous form by taking the real part of all of this guy e to the power j omega t, you will find that the definition of this guy and this guy only change with x and y, so it will move up and down. But the wave along z direction or along positive z will give you the definition of cosine omega t minus beta z. In fact, this component, this part here, omega t minus beta z, because all of them is inside the argument of cosine, it means clearly that the wave will be propagating as time progresses. As time increases, this wave will be propagating along positive z. What about if I take this part, if I make it like this? So it will be like cosine, cosine. What's this cause propagation? So I split the cosine. Now I have cosine omega t and the cosine beta z. What's this cause propagation? So with time progress, if the time keep increasing, would this wave move along the axis? No, it will not move. Most likely it will not move. Because both omega t and z must be inside the argument of cosine. This is what will cause wave propagation. So as you can see, this is the only part which will be propagating. So by assuming t here equal to 0, or t over 8 and t over 4, so we can start by assuming t equal to 0. Then you use this, sketch this function versus z, versus the space coordinate. You will find the function is here, this at t equal to 0. Then the second one at t equal big T over 4, or big T over 8. Third one at t equal big T over 4. T is the periodic time. So as the time increases, the wave is propagating along z, and then now we can calculate the wave velocity. How can we calculate the wave velocity here? So if you take any point here on the wave, this point at different time has the same magnitude, right? This point z call it equiphase point. So the phase here must be the same at different times. This means I can assume that cosine omega t minus beta z is constant at different time and at the same point, zb, at this point, at zb, which does increase by time. Okay? And then take the derivative with respect to time. This will give you dz by dt, the wave velocity is omega over beta z. So why did we choose this solution? So let's go back to this structure. So we have metallic hollow tube. So the wave clearly will be propagating along negative z. The wave will go this direction, and we are going to have some reflection from the side walls. So these side walls will cause some reflection, right? And the wave will be propagating along this direction. So it's more appropriate, more common sense to choose standing wave along x and y direction and the traveling wave along z direction. This is based on the structure itself. In another problem, we could have something else. But based on this structure, because the wave bounces back and forth between these walls, so it will make sense to have standing waves along x and y direction and propagating wave along z direction. So the solution, after we solve Maxwell equation here, subject to boundary condition, we will have this solution. We have standing wave along x and y and traveling wave along z direction. So this is a solution for this case. Now we move to source free. So no electric current, no magnetic current, no electric charge, no magnetic charge, but lossy media. What's the meaning of lossy media here? What is the consequences of having lossy media? So the wave will be decaying along the space direction. So as the wave travels, it will decay, it will lose energy. And this energy will be absorbed in the medium itself in the form of heat. It's like I square R, like ohmic losses. So the only difference here is that instead of using beta square, like what I have done before in source free and the lossless medium, here I'm using minus gamma square, which is the original equation I have got from the wave equation. This is the original wave equation. Gamma square here is the propagation constant, g omega sigma minus omega square mu sigma. So I can take g omega mu out. And now we need to solve this equation. If sigma equal to 0 here, what will be gamma square? If sigma is 0. Gamma square will be minus omega square mu epsilon, which will be plus beta square. This part now will be plus beta square, which what we had last time. So sigma equal to 0 will take you to the same condition we had before. So now look at this equation here. I'm going to replace E by Cartesian coordinates, this E and the other E also with the same. So this E is here and this E is here. Now I'm going to equate the X component together. Okay, so this part here, del square EX will be EX times minus gamma square, right? Why this should be correct? And look at these three equations. These are three scalar equations that have been produced from the wave equation, from the vector wave equation. We have now three scalar equations. Why this equation is correct? Why am I able to equate the X component here and here? So the question again, I have taken this part and assume it's equal to this part, because both of them are multiplied by AX. Here I'm assuming that AX is constant. Is it true? Is AX is constant and AY and EZ? What makes them constant? AX, AY, EZ. So if we think about the Cartesian coordinates, in Cartesian coordinates we have like X, Y, Z. If you pick some point here, B1, some point with X1, Y1, Z1, what's the direction of AX here? What is the direction of AX? In this direction, right? And AY in this direction, and EZ in this direction. If this B moves here, now B is here, another point, B2, X2, Y2, Z2. What is AX here? Same, right? AY, same, EZ, same. This fact, or what we have here, is that for at different location, AX is parallel to each other, AY is EZ in parallel, so we are capable of doing this, of transforming this equation into three scalar equation. Okay? Because AX is the same everywhere, AY is the same everywhere, EZ is the same everywhere. Now, this is Cartesian coordinates. In cylindrical coordinates, can we do this? يعني assuming now we are solving for cylindrical coordinates. In cylindrical we have rho phi z, right? And in spherical we have r theta phi. Can we do this in cylindrical and spherical coordinates?
Position change will cause theta change.
In either here. The question again, if this field is in cylindrical or spherical, can I take, if this is a rho, so instead of ax and ax, I have a rho, a phi, easy. Can I directly take the three equation from the mother equation? Yes or no?
No.
Why no?
Because in cylindrical coordinates, phi is always tangential to the.
So
It will always.
why? You know?
Yes. If we have a cylinder, the cylinder coordinates the direction of the phi, you said it's tangential to the radius. So if we are at the left, if we are sorry at the right, the phi will be.
So assuming we have a point here, yeah, okay, continue. So assuming we have a point here, what is the direction of arrow? Where's arrow here?
Inside.
Huh?
The arrow is out to the right.
Arrow is here, right?
Yes.
And
A
a phi,
inside
if I will be something like this, or tangential to this guy, and AZ will be here up there. Now this B comes here. I have now B2. Where's arrow?
to the left.
Something else, something totally different. They are not the same. It's like arrow phi. Whereas a phi, something somewhere else. Easy is the same. Easy agree. Arrow and phi is something different. So I can't do this if you are in cylindrical coordinates. It will be much tougher than this. What makes it easy is that ax is constant, ay is constant, az is constant. Today, now we are going to move to cylindrical coordinates, and you will see the difference between Cartesian and cylindrical. So what makes Cartesian coordinates easy is that you can easily take ex, the x component, to be the same y component, z component. Now we need to solve this equation. We'll do the same. We are going to have three scalar equation, but here I have gamma x, gamma y, and gamma z, and I'm going to use the separation of variable. So I will have f, g, h. F will have two forms. Traveling wave and standing wave. Traveling, standing. But here I have hyperbolic trigonometric function. I have cosine, not cosine. I have cosine and the sine. And the final answer will be, again, you need to choose whether you take F1 or F2, because you have traveling wave, standing wave. You need to wisely choose which wave you will choose, based on your problem, based on the situation. And here's the constraint equation, like the equation we had before, but I will have here gamma x squared plus gamma y plus gamma z equal to gamma. This means the vector gamma, the propagation vector, must have the same direction regardless of gamma x, gamma y, and gamma z. Sorry, must have the same magnitude. Yani the three component will add up to the same magnitude of gamma. So even for different gamma x and gamma y and gamma z, they must add up to the same propagation constant. This means, again, gamma vector will be, for any value of gamma x, gamma y, gamma z, gamma vector will be like on the surface of a sphere, lies on a spherical surface.
Can I ask a question?
Yes.
We introduced that cosine and sine because of the gamma is complex, right?
Yes.
Okay.
Gamma here, gamma square, if you remember, from Maxwell equation, from Faraday's law and Ampere's law, it was based on sigma. So gamma will be plus negative square root of all of this. We have here two components, right? We have inside the gamma, we have two things. We have this guy and this guy. So what's the difference between them? What does sigma here represent? The loss mechanism. The wave is decaying because of sigma. If we don't have sigma, there's no decay. And what does the other guy represent? The wave velocity and the phase accumulation. As the wave is traveling, it will lose some energy and it will accumulate some phase. The phase will keep increasing by time based on this parameter, omega epsilon, omega root mu epsilon. So we have loss mechanism and propagation, or wave velocity and phase accumulation mechanism. Here, sigma could be positive, could be negative. For positive sigma, this equation will end up by alpha plus g beta. That could be positive or negative. For negative sigma, this equation will end up as plus negative alpha minus g beta. This means the gamma can have one of four solutions. Gamma can have this guy or this guy, this guy or this guy, based on positive sigma and the negative sigma. What's the meaning of negative sigma? So positive sigma is wave attenuation, decay, right? So what is negative sigma? What does negative sigma represent? Mathematically, think about it from mathematics point of view. Yes.
Actually, it means that the wave is increasing, not decreasing, with the exponential. Because if the alpha, the real part is positive, this means it's exponential increase.
Yes.
So somehow it's related to something that have a gain.
It's hypothetical, correct. It's hypothetical concept. If sigma become negative, this means the wave will gain energy as it travels. It's like active medium, okay? Which against truth, we don't have this unless there is continuous source of energy. As long as the wave is propagating, there is another source of energy increasing the wave. Mathematically, we can accept this, but physically it doesn't exist. We don't have active medium. The medium we are seeing around are passive lossy medium. So sigma must be positive. But in case sigma is negative, you will have this solution plus alpha and the negative alpha, and this will cause wave increase as it travels. This is a mathematical concept, and it will be clear here in this part. So this is what I said. So assuming for some problem, I'm going to choose standing wave in x and y direction, and propagating wave or traveling wave along z direction. Then I'm going to pick the this part. I'm going to assume this part doesn't exist. This is the wave propagating in negative z. I will assume it's not there. I will only take this part, which is the wave propagating along seemingly positive z. Now, if you remember, gamma has like 4 different solutions. Gamma can be this, can be this, can be this, can be this. Based these 2 guys for positive sigma, these 2 guys for negative sigma, which is hypothetically mathematical concept only. So look at this 4 different solutions for the wave propagating along z direction. So now I have split alpha from beta. So what does each part represent? Here, the first one, what does this represent? A wave propagating along positive z and decaying as it travels, right? Next one, along negative z, wave propagating along negative z and decaying as it goes. It's still decaying because z is negative here. يعني I know the wave direction from this part. This part first tells me the wave propagation direction. Then the second part will tell me whether it decays or it gains energy or it increases. So this guy, positive z propagation, and it does decay. This guy, negative z propagation, and it does decay as well. This one, propagation along negative z, and it will gain energy, like negative conductivity, which is mathematical concept. This guy, we're propagating along positive z, and it does gain energy. So these 2 guys gain energy. We assume it doesn't exist in reality. Again, unless we have like active medium that will add energy to the signal, which we don't have, something like transistor or MOSFET. So I'm going to choose one of them. I'm assuming that the wave is propagating along positive z, so I will exclude this. This is a negative z propagation. I will exclude it. I'm only working now with positive z propagation. So the most appropriate, the most logical solution is this solution. A wave traveling along a negative z with decaying amplitude, with decreasing amplitude. The other guys will be rejected. This also can be a valid solution if you assume the wave is propagating along negative z, or if you consider the wave reflection, because this is the incident wave, this is the reflection wave or the reflected wave. If you assume we have reflection, then you will have the other component, which again, wave propagating in negative z with decaying amplitude. And also this shows that the propagation is taking place in passive, lossy medium, and it does verify the law of conservation of energy. The energy cannot be created or eliminated. So this agrees with the law of conservation of energy. These 2 guys does not agree, because this means we need to add some energy to the signal. Okay? Now we go back to gamma. We need to split gamma into 2 components. So I have gamma here. I will assume sigma is positive. So gamma will be plus negative z square root. So I can take gamma square equal to square of this guy equal to this guy here. Then I will expand this part. So I will expand this square to be 1, 2, 3 terms equal to this guy. Then I will take the real part equal to the real part and the imaginary part equal to the imaginary part. From these two equations, I have two equations, two unknowns now, alpha and beta. Then you can find alpha and beta. Very direct. From these two equations, you can find the attenuation constant measured in neighbor per meter. Neighbor is like logarithmic unit. It's related to decibel. Okay, something like decibel, which shows a wave attenuation. And beta is the phase constant measured in radian per meter. Okay? Any question here? Does this equation make sense? Look at these two equations down here, alpha and beta. Do you think they make sense? Or do we make a mistake? We made a mistake? Look at anything. Do you think they make sense? Look at sigma. If we play with sigma, if we make sigma equal to 0, what will be alpha?
0.
So it makes sense. As the other equation down here, beta. If we make sigma equal to 0, what will be beta? If sigma is 0 here, all of this will be 1. It will be omega root mu epsilon, which is beta for in lossless medium. So beta here is based on sigma, on how much losses I have, and also the attenuation is directly proportional. The more sigma, the more attenuation you will have in your medium. Stop the video, Anas. So today we are going to move now to solve the wave equation, which is derived from Maxwell equation, but in cylindrical coordinates. Before doing this, let's visit Bessel function. Look at this second order ordinary differential equation. Y of y as a function. How can we solve this? How can we find y? Second order ordinary differential equation with b like some constant integer. How can we find y? Sorry? No. I mean, is there a straightforward way, like solving ordinary differential equation? Is there a straightforward way to solve it?
Yes, we have another way to have the poles for the equation, then we have the value for the natural y and somehow some steps like without the Laplace, we can solve the y that it has a specific value. If it's equal to 0, then we solve it with another equation.
Try it, but it will take time. What you are saying will take very long time. The standard solution based on Frobenius method is Bessel function. The solution of this equation, which is Bessel differential equation, will be Bessel function of first type, which is Jn, and Yn Bessel function of second type. It's like a standard function that we can use to solve this differential equation. Maybe the solution, what you are saying, will end up by this, but we are not going to go through the steps. We'll take it that assuming b equal to some n integer, because there's another solution when b is not integer. But let's focus on the integer b. So on the integer b, assuming b equal to n, it will be based on Jn of x, which is Bessel function of the first kind, which is this equation. Jn of x equal to this guy, assuming n equal to b. So it's minus 1, it's summation from m is 0 to infinity, minus 1 power m, x over 2 to m plus by, factorial m plus b. This is Bessel function of the first kind, call it first kind of order b. B here can be 0, 1, 2, this is the order of the function. And each order will have different field distribution. The other guy, Yn, is Bessel function of the second kind. So it somehow has some similarity with GB. Again, this is Bessel function of the second kind of order B. So look at these two equations. Are they related somehow? So actually, Bessel function of the second kind is based on Bessel function of the first kind, GB, and also based on the Bessel function of first kind with negative order. We have here negative B. So what is G negative B? This is G of order B. What's G of negative B? The same like this, but just to make B negative. Okay, so the solution of this second order ordinary differential equation will end up by having the same form of Bessel function. How does this relate with electromagnetics? Actually, this equation describes the field propagation in cylindrical coordinates. After we build the problem and solve the wave equation in cylindrical coordinates, we'll end up by an equation like this. So we can directly use the Bessel function to find the solution of this equation. Okay, no need to go through the steps. We'll just use the solution as it is to find the field. This will be like E or H in cylindrical coordinates. So let's take some insight to understand Bessel function phase second kind. So it's important to find the value of J and Y when X becomes very small or very large. So when X is approaching 0 and X approaching infinity, we need to see what is the value of J and Y. When X is approaching 0, look at this equation, put X equal to 0 here. When X equal to 0, what will be J0 of X? So X is 0 and B is 0. Or X is approaching 0 and B is 0. What will be the summation? It will be 1, okay? So the Bessel function of the first kind of order 0, when X is approaching 0, when X is very small, will be 1. Bessel function of the second type will be this equation, 2 over pi ln gamma x over 2, and the gamma is constant. So if X is 0, what will be Bessel function of second kind? What will be Y0 if X is 0? Huh? Put X equal to 0 here, says the ln. Y will be minus infinity, ln 0, okay? So it's like singular function. And this is singular function because it is not defined, it's minus infinity. If X approaches 0 and the order becomes bigger than 0, this order B, so we are studying B equal to 0, order 0, then higher order when B gets higher than 0. The same equation we have, so when X is approaching 0 and B is bigger than 0, GB what will be GB of higher order? So assuming B anything bigger than 0. GB, when X is approaching 0, GB will be always 0. It will be like this, something like this. So this is a Bessel function of the first kind of different orders. So I'm just sketching this equation. Look at this equation. I'm just changing B, the order from 0, 1, 2, 3, and I'm sketching J versus X. So this is what I will have. So at X equal to 0, G0 will be 1, as we have seen here, if you remember. When X is approaching 0, G0 is 1, and all other Bessel function will be 0. Then as X increases along the spacing X, Y, Z, assuming Z here, the wave will be like decaying with the distance and also oscillating. So we have oscillation, something like cosine and sine, and we have attenuation. So there is some similarity or big similarity with wave propagation. It is oscillating, sine, cosine, and it does attenuate with time. So when Z goes to infinity, what will be the function value? It will be 0. When you go to infinity, all these guys will be 0. Again, this will be the field in cylindrical coordinates. This will be the solution of the field of the traveling waves in cylindrical coordinates, which does agree with what we understand about the wave, phase accumulation and attenuation. So if I'm going to make this bigger, so here I have Z from 0 to 20, I'm going to make it from 0 to 50. What do you see here? So again, I have a Bessel function of the first kind. Again, this is solution of the second order differential equation we have seen, which will be the solution of the wave equation in cylindrical coordinates. So we're going to use this. So here I'm using Bessel function of first kind, J, with different orders, 0, 1, 2, 3, along X, or along the spacing X. So what do you see here? As X increases, this function, are they behaving in the same way? So what's the difference between them? As X increases, when you go in this direction, how does this waves or this function behave? Actually, as the order increases, if you look here carefully, as the order increases, the number of zeros of the function increases, the number of oscillation increases. And when you go from G0, 1, 2, 3, 4, and higher order, you will see that the oscillation increases with the order, and at the end, all of them will approach 0, or this function will approach 0. What else you see here? The oscillation actually, yeah, and here the oscillation is not very clear, but as x increases, you will see like very similar to sine and cosine. As x increases or as the distance increases. Anything else you see here in this special function? What about the other guy? So again, the solution of this second order differential equation is two functions. Bessel function of the first kind, which we have seen, and then we have Bessel function of the second kind. We have seen the behavior of this guy that when the order is 0, the function equal to 1 at x equal to 0, and when the order anything bigger than 0, the function equal to 0. What about the other Bessel function, the other part, yn? Yn, how does it behave along a distance? So I'm going to increase the order, b, 0, 1, 2, 3, and so on, and see how this wave behave. Bessel function of the second. So this Bessel function of the second kind, which is y0, y1, y2, y3, which again is related to Bessel function of the first kind. But look here at this behavior, look at this part here, when x is 0, when x is 0. If you use the equation we have seen at the beginning, all Bessel function of the second kind will approach to negative infinity. All of them is negative infinity. Until x increases, then you will have some kind of oscillation. And again, as x increases, the wave will decay. So we have oscillation behavior, cosine, sine, decaying behavior. And as x increases, the oscillation will be more dominant or clearer. You will see clearly we have oscillation here compared with this part. And also, as the order is this time subscript here, 0, 1, 2, 3, 4. As the order increases, the number of oscillation increases. Okay? This will be the field. This will be the field in cylindrical coordinates. Another solution that we can use other than Bessel function is Hankel function. The Hankel function is very simple, the complex combination of Bessel function. So we have a Hankel function of first kind, which is GB plus J YB. So it's very similar to or very related to the Bessel function of first second kind. Hankel function can be used to solve the second order ordinary differential equation we have seen. Okay, yeah, we have two solutions. One using Bessel function, one using Hankel function. Hankel function again has two order or two types, two kinds, kind 1 and kind 2. The only difference is this plus negative. Okay, and both of them will be used. Both of them will be used in our solution. So this is Hankel function of first kind, Hankel function of the second kind, and this is the definition when x tends to infinity. When x approaching infinity, Hankel function of first and second kind will be like what you see here. Again, when x tends to infinity, the wave will decay also. The wave will be very small. Now, math is enough. Now we'll go to our electromagnetics. Now we're going to solve the wave equation in cylindrical coordinates. Okay? What is the difference between Cartesian coordinates and cylindrical coordinates? Here, do you remember this guy? It was easy in Cartesian because AX is the same everywhere, AY is the same, is the same. But in cylindrical, it's a different story. A rho is not constant. In fact, A rho is based on rho phi z, based on the location. A rho is function of rho phi z, A phi function of rho phi z, only AZ is constant, only AZ is parallel. So I can simply solve, and that's what I will do. I will solve the equation for AZ, and I will try to attempt to solve the solution for phi and rho. So I'm going now to assume that I have some cylindrical structure, and I'm going to solve the wave equation, but assuming the electric field is based on cylindrical coordinates. You know cylindrical coordinates, right? So I have A rho in this direction, A phi in this direction, AZ in this direction. Can I replace phi with rho? Can I make A phi in this direction instead of this direction?
The same phi down? The phi is still down?
Same phi.
No,
Why?
because the phi is increasing this side.
This right hand rule, we can do this. A rho cross A phi must be easy. This is the same as AX cross AY must be easy. This is a right hand system we are using. Some other guys using left hand. If you are using left hand, you must reverse phi, but we are not using left hand. The right hand system must be based on this cross product. So a phi must be in this direction, which is the direction of increasing phi. But the dominant reason is that the cross product here must be easy. So the problem here is Laplacian operator. Laplacian operator del square E can be related to grad divergence and curl. Here we are going to, it will be very difficult to use this guy. I will use grad divergence and curl. So I will replace Laplacian operator by this vector operator, and that's it. This is the wave equation in cylindrical coordinates. So I will have del square E minus beta square E equal to 0. And I'm going now to replace E by cylindrical coordinates, E rho, E phi, E z. So E will have 3 components, as you can see. Then I'm going to plug this E here in the wave equation, right? Then what? What should I do next? I have used the wave equation with E defined in cylindrical. Then what should I do next? How can I proceed here? What did we do in Cartesian coordinates?
We equate with the directions, but we cannot do it.
So what should I do?
We change the Laplacian.
Huh?
We will change the Laplacian.
So I have a rho here, and I have a rho here. It was easy in Cartesian because in Cartesian I took this guy out, right? Because it's constant. Here I cannot take this out because it does the a rho here is function of rho and the phi and z. Like here, look, at different location it has different direction. So I cannot take this out of the del square. It has to be inside. Being inside will make things very difficult, a little bit difficult. So now here, these two guys are not the same. These two guys are not the same. These two guys are the same. Only z can work. Ez is constant. I can take ez out. But these two guys will not work out. So I have to go away from Laplacian operator and use the grad divergence minus curl. So I will get rid of this guy and I will use grad divergence and curl. So the wave equation now will be, I'm going to replace the del square by this guy. Okay? Then, what's next? I need to solve for E rho. I need to find E rho and E phi and E z from this equation. What should I do? One common sense solution is that I'm going to assume that E is 3 component and substitute E in this equation. So I will substitute E here. When I substitute E here, I will find the definition of del square for Cartesian for cylindrical coordinates. Look at this equation. This equation, once I substitute E in the original equation, I will see that del square E rho will be here. So this will give me equation based on E rho, and I will find del E phi, del square E phi here, and I will find del E z minus beta E z square here. This based on the definition of Laplacian operator for cylindrical coordinates. So again, I will have like 3 equations. One equation will be based on E rho, but looks difficult here. We have E rho and E phi in the same equation. It was not like this in Cartesian. Here also I have E phi and E rho in the same equation. Only this guy I have only EZ, one unknown only here. So I can manage with this guy. But how can I solve these two guys? Yeah, look at this two equation here. They are coupled equations. Coupled means I have E rho and E phi, E phi and E rho in the same equation. Only this I can do because I have only EZ. So let's see. We can again here when I substituted E rho in this equation, I have to use the definition of del square psi, or this is a scalar operation of Laplacian for scalar quantity, which is like E rho, E phi, E z. So assuming that easy here like scalar quantity, so I can now replace del square psi by the differential of the Laplacian operator for scalar quantity. Then I can use the separation of variable to solve for easy, like what we have done before. This is the same as we have done before. So I will start by this. I will start by solving for easy using the separation of variable. Okay. So del square psi equal to all of this. Then replace psi. Psi is easy. Psi here is easy. Okay. And I'm solving for easy actually. Psi here, same as easy. So I'm going to assume easy is FGH, then substitute here, then divide by FGH. When you divide by FGH, you will get this guy here, right? So look at the last term. The last term is h, and h is function of z. And we have dh by dz. So this function is based on z only. And it is added to some other function, and all these terms must equal to some constant. So I can assume this guy to be constant as well. Every term will be constant actually. So I'm going to assume this to be constant, which is minus beta z square. So I can now work with this guy to find h. H here is h of z. This is a part, the z component or the z function of ez. I'm assuming ez is like 3 function. So I'm going to find h from this equation. After I do this, I can now the same equation here. I will get rid of rho, so I will divide by rho square. Here, look here, because I have rho square here, I can get rid of this guy. So multiply by rho square. So I will have rho square here, and rho square here, right, and rho square here. Rho square times minus beta z square. When I get rid of rho square here, this part here will be function of phi only, because g is based on phi, and also have dg by d phi. So this guy can be assumed to be what? Some constant as well, because all of these are constant added to find to end up by some constant. So so after multiplying this equation by rho square, I will have a function only based on phi, which I can call minus m square, minus any constant. So this equation now is minus m square, which I can work with. I can now solve this equation to find g. Yeah, things are starting to be easy. Now I can find g, and I already found h from this equation. This equation can help you to find h, same as Cartesian. And this equation can help you to find g. So after replacing this part, which is based on phi only, by minus m square, and this part by beta z, I will end up by these two guys. I still need to find f, because ez is fgh, right? So h is already done from this part. H can be found from here, and g will be found from this equation. It will be very similar to what we have done before. What about f?
Can I ask something about the m?
Okay.
The m square, we assume that the other side will be also constant, like the rho square is constant.
It is constant, but if we assume it to be constant, it will be like oversimplifying the equation. This part is constant. But if you go in this direction, it will be like oversimplifying the equation, it will lead to inaccurate solution. But if you substitute this part by minus m square, and part by minus beta z square, look at this equation now. This equation is Bessel differential equation, the first equation we have taken. So I can use Bessel function now to give you more accurate solution. But this part is constant as well, because it will add to constant. But if you take it as a constant, it will lead to inaccurate solution. It will be like oversimplifying the equation. But we have already standard solution, which we can use directly, which is Bessel equation of first kind, second kind. You don't need to assume this to be constant. Again, this will be like oversimplifying this equation. So after solving for m and the beta z, I can now solve this as Bessel function. Multiplying by f, to get rid of f here, you will multiply by f, And assuming now that beta, this part here, beta square minus beta z square to be beta rho. Okay, we don't have beta phi, beta rho. So beta rho square will be beta minus beta z square, and this will be our concentrating characteristic equation. You remember beta x, beta y, beta z? You have beta rho and beta. We don't have beta phi because beta phi is like a periodic rotation. So I have beta rho plus beta z equal to beta square. I'm going to replace this by beta rho. This is exactly the same equation, Bessel differential equation, which can be solved using the Bessel function. Okay, so you don't need to assume the constant relation. You don't need to do approximation when we have exact solution.
Okay, so M is not a constant.
No, m is a constant.
From here, the right side.
Because here, look, yeah, this situation, I have only one part of differentiation. Here I have d by d and d square by d square.
Okay.
So both of them can be assumed to be constant, but again, it will be oversimplifying the equation. When I have exact solution, why I need to go and assume this part to be constant? When I can solve the equation in an exact way. And here I have only one part of differentiation. Here I have two parts. So it will again complicate the equation, even if I assume constant, it will be complicated as well. And solve this won't be easy. Try to solve it. Try to assume to be constant and solve it. So I'm almost done with G and H, and this is the solution of F will be Bessel function. Does this make sense? So let's summarize what you have been saying. So I'm going to use the Laplacian operator in cylindrical coordinates. This will give me the first equation we have assumed to be constant, minus beta z. This will give me hz. What will be two solutions, the same as we had before, traveling wave and standing wave. Also, G will be the same as we had before. Look at these two equations, same as Cartesian. The only new thing here is solving Bessel equation to find F. And we have also the concentrating equation, which relate beta rho and beta z with beta. This is summary of what I have been saying. So what is the solution now for H and G? So I'm trying to solve for psi. Psi is F, G, H. F will be from here. G will be from this guy. And H will be from this guy. So I can now find H, which will be two solutions. G and also F of rho will be two solutions as well. One using Bessel's, other using Hankel function. So the first part to solve for H, I will have two equations. Traveling wave, because I have complex exponential. This must be traveling wave. In lossless medium, we have lossless source-free medium. And this is standing wave. And this is a concentrating equation. For M, or for G, to solve for G, G as a function of phi, again, will be traveling wave and standing wave. The same as we did in Cartesian. Now for the last part, which is F, this is exactly Bessel differential equation, and the solution will be either based on Bessel function of first kind of order M, Bessel function of second kind, Hankel function, or it will be like this or this. This is Hankel function of first kind, Hankel function of second kind. So again, we have two solutions. With different constant here, I have A1, B1, C1, D1. So let's see. So this is the final solution. F will have two form, G will have two form, H will have two form. So based on what I can choose the solutions we have here. So I need to choose one of these, one of these, one of these. Based on what? Based on the problem itself. So the Bessel function, first and second kind, will represent standing wave. Hankel function will represent traveling wave. It has the attributes of traveling wave as a standing wave due to the reflection at the boundary. This guy, again, the complex exponential is traveling wave, and this guy is periodic wave. We call it periodic wave, something like standing wave, but we call it periodic because it is based on phi, so it will take the rotational direction. HZ will be traveling wave and standing wave. The reason that H here is traveling wave because it is a complex combination of Bessel function. You remember Bessel function? Bessel function was like summation of some exponential and factorial. But H is complex combination. Making it complex, it's like y, like j plus jy, h, will give it the feature of traveling wave. Are you getting this? Again, h, this function, is a complex combination. It's like j plus jy. So it will give the attributes or characteristics of traveling wave. Okay. So this is, again, this is what I was saying. This is a Hankel function of first kind. Again, complex. This j here makes it traveling wave. And we have the second kind, we have both plus and negative. For e to power j omega t time variation, this guy will be traveling in negative rho, this guy will be traveling in positive rho. Something like e to the power minus z and e to the power jz. So one of them negative rho, one of them positive rho. This is based on the function behavior. This is the definition of the function. Okay, and based on this definition, this guy will be traveling negative rho and positive rho. So if I'm going to solve the wave equation in a cylindrical hollow tube, this is what we call circular waveguide. So I need to solve for E and H inside this circular waveguide. I need to solve Maxwell equation subject to the boundary condition. The boundary condition is that E tangential on this surface is 0. So I'm going to solve the wave equation in cylindrical coordinates. Now I need to choose one solution for F, one for G, one for H in this structure, cylindrical hollow tube. Which solution I should choose for rho? For rho, which one I should choose? Standing or traveling? Guys here. For rho direction, do you remember rho direction? Rho direction is like, so this is a cylinder. So where is the rho direction? This is like rho direction, and the phi direction like this, and z direction will be along this guy, right? So rho direction, the wave will go back and forth, bouncing between the walls. So like standing wave, it will go nowhere. So I'm going to choose this for the rho direction. What about the phi? We don't have standing wave, we have traveling wave and periodic wave. Periodic means rotational wave. So it will be like this guy. For the z direction, traveling wave. So this is the three solution I have. Okay? This is the, so the solution is based on the structure, the problem you are solving. So in rho it will be standing wave, and in phi it will be like periodic wave. Cosine and cosine will keep rotational, and in z will be traveling wave. This will be the solution in this cylindrical waveguide. We are going to take this in details in chapter 8 or 9. We're going to find the full solution for cylindrical waveguide. Any question? You are with us? Okay. So if we are working inside the waveguide, I'm going to assume that the wave is moving in positive rho. So in positive rho, I will have this variation. Okay. And also, you remember the behavior of the Bessel function. M here, Gm must be not 0 at rho equal to 0. Okay. You remember this? So Gm here must be bigger than 0, because when m is 0, it will give you this function equal to 0. Remember the behavior of the Bessel function? So this is a Bessel function. So when the order is 0, you will have 0 function. So this is like the axis of the cylindrical waveguide. When rho equal to 0, you will have 0 field. So we must exclude this guy and consider only the higher order Bessel function, which is like, sorry, it's the other way around. So I have to exclude this, and I have to use G0, because G0 only give you non-zero field value. I have to exclude the other guys. The other guy give you 0 field at the origin. At the origin means at the core or at the axis of the cylindrical waveguide. when rho equal to 0. And I have also removed ym, because ym equal to, if you remember the Bessel function, the solution was gm plus ym. But I have to exclude ym because ym will be minus infinity at rho equal to 0. Remember the singularity, the second type, it was minus infinity. So I have excluded it from here, so I have gm. This is the wave traveling inside the waveguide. What about if I am solving for the wave outside the waveguide? Outside the waveguide, I need to choose Hankel function, because this function is standing wave. So outside the waveguide, the wave will be like radiating away from the waveguide. And assuming the waveguide is like a source or a scatterer that sends the wave outside. So if you are outside the waveguide, we are going to replace the Bessel function by Hankel function. Why am I using Hankel function here? Because this is propagating wave or traveling wave along positive rho. So I'm using the second type. I'm using the second kind of Hankel function, because this is the propagation along positive rho. So this is the field definition inside the waveguide. This is the field definition outside the waveguide, which does represent outward traveling wave. This will be like outward traveling wave. So I have to choose Hankel of second kind, which will give you the propagation along positive rho. Thank you.